All right, we're going to go over the concept of momentum and change in momentum. So on your quick start, you should have answered the question, which is more difficult to stop? A tractor trailer barreling down the highway at 35 meters per second or a small two-seater sport car traveling at the same speed? And you probably know intuitively that the tractor trailer is going to be harder to stop. But why is that? It comes down to a concept called momentum. And momentum is just the quantity of motion of a moving object. It is a very simple concept, and it's just a way of putting a number to motion. And we sometimes call it inertia in motion. So if you remember Newton's first law, where we talked about how an object has inertia, and inertia is the resistance of an object to changing its motion. And so an object with more mass is going to have more, or is going to be more difficult to either start moving or stop moving. So with momentum, sometimes we're just looking at that mass in motion or inertia in motion. So momentum is again just a way to assign a number to how hard it is to stop an object. So the simplest way to define momentum is it's a way to assign a number to how hard is it to stop something. The more momentum an object has, the harder it is to stop it. Now, momentum is a vector. That means that the direction matters, and the object's momentum is always in the same direction as the velocity. So if it's moving east, then the momentum is to the east. If it's moving to the west, momentum is to the west. If it's in the positive direction, momentum, or if the velocity is positive direction, momentum's positive direction. The momentum and velocity always have the same direction. Now, the formula for momentum is mass times velocity. So momentum has a variable that doesn't necessarily make any sense with the word. The variable is the lowercase p, and really the reason for that is it's a very fundamental concept that Isaac Newton thought was so basic, he just called it progress. So supposedly that's where the p came from. The equation, again, is just momentum is mass times velocity. So we just take an object's mass and multiply it times its velocity. The units for momentum are a little bit weird. So we have two different sets of units that basically mean the same thing for momentum. We can either have kilograms times meters per second, which comes straight from the momentum equation, because the units for mass are kilograms and the units for velocity are meters per second. So it comes straight out of the equation. Or we could also have it as newtons times seconds. We will mostly see this in our next video when we talk about a concept called impulse. But these two sets of units are functionally equivalent to each other. Now, with momentum, you can also solve for the speed of an object if you know the momentum. And this is the variation of the equation that you would need to do that. Or if you know your momentum and your speed, you could also solve for mass. And so this is the variation of that. So let's go ahead and do a couple of practice problems. And we will start with practice problem 1. And this is going to come from the initial practice problem or the initial quick start you did. So we have the tractor trailer barreling down the highway at 35 meters per second, and the truck has a mass of 2,000 kilograms. We want to know what's its momentum. So when you're doing these problems, when you see your numbers, make sure that you circle them or put a box around them. Or in the case of the electronic ones, you might want to just write them down, make a note of them. And we talked in the last session about identifying our units. If we have units of meters per second, this is going to be a velocity. And so our velocity is 35 meters per second. Here we have units of kilograms. Kilograms indicates mass. So the mass is 2,000 kilograms. So momentum is mass times velocity. So to solve the problem, we're going to do momentum is equal to mass times velocity. We're going to substitute our 2,000 kilograms for the mass, and then our 35 meters per second for our velocity. multiply 2,000 times 35, and that will give us 70,000 kilogram meters per second. So that is the answer to this question. So now let's look at the car and the same problem that we had in the beginning. The car, however, only has a mass of 1,000 kilograms. So this is the mass of the car. It is still going at the 35 meters per second. So momentum is equal to the mass, 1,000 kilograms, times the speed, and the momentum is going to be 35,000 kilogram meters per second. Now we could compare the two problems, and remember the truck was 2,000 kilograms times 35 meters per second, and it gave us a momentum of 70,000 kilogram meters per second. And so another kind of question you might be asked is if you look at the two masses here, the mass of the truck is 2 times bigger than the mass of the car. So this one was the car, this is the truck. So the mass of the truck is 2 times bigger than the mass of the car. So look at what that does to the momentum. The momentum of the truck is also exactly 2 times the momentum of the car. And that's because of the equation, momentum and mass are directly related. So if the mass is 3 times greater, momentum is 3 times greater. If the mass is 4 times greater, the momentum is 4 times greater. They're going to be the same. Whatever I increase the mass by, I'm also increasing the momentum. Now, another way we could do this is we could say, what would the velocity of the car need to be in order to have the same momentum as the truck? The car can have the same momentum as the truck. It's just going to have to move faster. So the momentum of the truck was equal to 70,000 kilogram meters per second. And we know the mass of the car is 1,000 kilograms. So using the equation that I gave you earlier, the speed that I'm going to need to have is going to be the momentum divided by mass. So that's 70,000 kilogram meters per second divided by our 1,000 kilograms. And that means that the car would have to be going 70 meters per second to have the same momentum as the truck. Now, something else that we can look at with momentum is we can look at objects when they change their momentum. Anytime an object changes its velocity, it will have a change in its momentum. Now, change in momentum we often do is, well, we usually write as delta P. Remember, this little triangle shape is delta. And whenever you see delta, that means it's whatever it's attached to, it's the final minus initial. So with momentum, we can plug in the mass times your final velocity minus mass times initial velocity. So this is the equation that we can use to find our change in momentum. Now, another thing to remember though, the direction matters. So this is going to be big on the problems we're going to be doing, and I will show you in the next two examples how to take it into consideration. So practice problem number 4. We have a 750 kilogram car. So kilograms again, that's mass. And it's traveling at 30 meters per second. So this is our velocity. But now the car slows to 15 meters per second. So we want to know what its change in momentum is. So remember, change in momentum is equal to mass times the final velocity minus the mass times the initial velocity. So we need to know which of these is final, which is initial. So we slow to 15, so this is where we end up. We start at 30, so that's where we begin. So I'm going to go ahead and plug in numbers, but no, never mind, just plug in the numbers. So my mass is 750 kilograms times my final velocity, which is 15, meters per second, minus my mass, 750 kilograms, times my initial velocity of 30 meters per second. So my 750 times 15 is 11,250 kilogram meters per second, minus my 750 times 30 is 22,500 kilogram meters per second. And if I subtract the 11,200, take the 11,250 and subtract the 22,500, I'm going to get a change in momentum of negative 11,250 kilogram meters per second. That negative sign must stay there because that shows that my change in momentum is in the negative direction. I reduced my speed, and so to do that, my change in momentum had to be pointing towards the negative direction. So when you answer these problems, if you get a negative, you must leave it there. So let's do one more. This time we have a half a kilogram baseball, that's 0.5 kilograms, and it's pitched at 45 meters per second, and it's hit back the other direction by the batter at 60 meters per second. We want our change in momentum. So change in momentum is the mass times the final velocity minus the mass times the initial velocity. So looking at the picture down here, we have the ball that's being pitched and we have the ball that's being hit back in the other direction. When it's initially pitched, it's pointing in the positive direction, so that's going to be a positive 45 meters per second. When it's been hit backward, it's now going to be in the negative direction, so that's going to be a negative 60 meters per second. So when we plug these numbers in, we have to keep that positive and negative. So we're going to plug in our mass, that's our 0.5 kilograms, times the final velocity, which is negative 60 meters per second, minus our 0.5 kilograms times our initial velocity of 45 meters per second. So our 0.5 times 60 is going to be negative 30 kilogram meters per second. And our 0.5 times 45 is going to be 22.5. And when I combine those, it's going to be a negative 52.5 kilogram meters per second. So you have to keep the negative sign. It means the change in momentum is in the negative direction. So go ahead and work on the practice problems. And if you have any questions, let your teacher know.